Okay, hi everybody. This is Merlijn from the Netherlands with a video on the importance of matching phase slopes, overlapping phase traces with matching slopes. It's a video that I made to accompany this article on my website. Michael Bink Knowles was kind enough to allow me to make the warbles available for download, and the warble is a better signal to phase align your main speakers to a subwoofer whenever you're pressed for time and do not have opportunity to turn on the analyzer. And it's a better signal than a sine wave, because a sine wave only exposes you to a single frequency, the frequency of the crossover, but not to all neighboring frequencies. And if we're not using a warble, then we will not be able to hear some potential problems when our phase slopes aren't matching or when the phase traces aren't overlapping. So a video to go with this article, and you can see the video already at the bottom of the page, but that's the one without the voiceover, and that's the reason why we're doing this video. So let's go back to this screen. We have Smart running up in the top right corner. We have Reaper running in the top left corner, and two plugins, or more important, two instances of the same plugin and another plugin. Over here we have delay, which is currently set to the subwoofer channel, and these are our crossover filters in the bottom of the screen that I've used to make a textbook crossover at 100 Hertz. And in the bottom right corner we have this table, and basically what it tells us is the amount of time offset required to introduce a certain amount of phase offset expressed in degrees. And the reason I chose 100 Hertz is because it has a easy to memorize 10 millisecond period. So 0 cycles offset, that is no time offset, equals 0 degree phase offset. And half a cycle offset equals half a period, or 5 milliseconds. Expressed in phase, that would be 180 degrees of phase offset. 1 cycle offset evidently is 10 milliseconds of time offset, and 360 degrees of phase offset. And 1.5 cycles is 15 milliseconds, or 540 degrees of phase offset. And finally, 2 cycles time offset equals 20 milliseconds. 2 periods of 100 Hertz, or 720 degrees of phase offset. So that 10 millisecond for a frequency of 100 Hertz is a very convenient figure to do some experimentation. So let's listen to some pink noise. When I press play, we will hear pink noise. And let's turn on the analyzer. Currently we have channel 1, which is our virtual subwoofer, and it goes all the way to 100 Hertz. You can see that we have -6, or if we introduce 6 dB of level offset, we can see that we have a -6 dB point at 100 Hertz. And this is your typical 4th order Linkritz-Riley low pass filter with a slope of 24 dB per octave. And that means that when I go 1 octave up from 100 Hertz all the way to 200 Hertz, you can see at the crosshairs that we are at -24. Channel 2 is our virtual main speaker, and it's the same topology, it's the same Linkritz-Riley filter with the same corner frequency. Again, a -6 dB point at 100 Hertz, and if we go down by 1 octave down to 50 Hertz, we can see that we also have lost 24 decibels. So that is our textbook crossover, and if we combine these two signals together, we will see summation, and if I make them equally loud, we can see that we have a nice bridge covering this gap. Exactly what we're trying to do when we're time aligning, or more important, phase aligning our main speakers to our subwoofers. So let's see what happens when we are in phase but not on time, which can be very much the case. Let's lower the phase graph by 180 degrees. I'm cycling through the y-axis, as you can see. So this is the default with 0 in the center, but let's lower the phase trace so we have 0 in the bottom and 360 degrees at the top. As you can see, we have nice matched phase slopes with overlapping traces. That is what we're trying to achieve. But what happens if we consult the table and introduce 5 milliseconds of time offset, half a cycle at 100 Hertz? So in the left we have a delay which is currently introduced into the subwoofer channel, or channel 1 if you will, and this is milliseconds times 1, and this is times 10 equaling 10 milliseconds, and this is times 100 equaling 100 milliseconds. So let's introduce 5 milliseconds of delay into the subwoofer channel, and you can see that where we had summation before, we now have cancellation. That is because by introducing that half cycle offset, we introduced 180 degrees of phase offset, and this means that we are no longer in phase. In fact, we are 180 degrees apart, meaning that we have cancellation, as is evidently in the combined signal, the red trace. However, this is the interesting part, if we flip the polarity of the subwoofer channel, then what was out of phase becomes in phase again. And you can see that we again have summation, even though we are half a cycle or 5 milliseconds apart in time. And this is shown by the intersecting phase traces at 100 Hertz. But the slopes do not match. The tangent to the main speaker, the blue trace, and the subwoofer, the green trace, their tangents are not the same. They do not have the same slope. And that is why we only see summation at 100 Hertz, and to the left and right of it what is known as frequency response ripple. And if we're listening to a sine wave, then this would not be obvious because we're only exposing ourselves to a single frequency. But in fact there is a whole range of frequencies that need our attention. All the frequencies where the level difference between the subwoofer and the main speaker is 10 decibels or less. So that's about an octave wide span that needs our attention. And we're not exposing ourselves to those frequencies when listening to a sine wave. So if we consult the chart and we take out the polarity inversion, then we will see cancellation again at half a cycle phase offset. Let's go to the next instance in the chart and let's delay the subwoofer by 1 cycle or 10 milliseconds. This would be the outcome, summation again, because even though we're 1 cycle apart, we are in phase. If we look at the green and the blue guy, we see that we have intersecting phase traces at 100 Hertz. But again, our slopes do not match. If we look at the outcome, at the combination of both signals, you see increased frequency response ripple to the left and the right of the crossover frequency. So let's go to the next value in the chart, which is 1.5 cycles or 15 milliseconds. So let's add 5 milliseconds, and now we will have cancellation again because we are now 1.5 cycles apart at the crossover frequency. But if we flip the polarity, then out of phase becomes in phase again. In phase, but 1.5 cycles apart. And if we look at the individual phase traces, we can see that they're intersecting at 100 Hertz, but their slopes are not matching. And this is the reason why we see frequency response ripple to the left and the right of the crossover frequency. And listening to a sine wave, as we will do in a little bit, will not reveal this issue. So let's go to the final instance in this chart, and this goes on and on clearly. Let's go to 2 cycles of offset equaling 20 milliseconds. So let's take out the polarity inversion and let's go to 20 milliseconds or 2 cycles of time offset. And again, you can see that we have summation. The phase traces are intersecting at 100 Hz, but their slopes do not match. As you can see, we now have severe frequency response ripple throughout the crossover range. And we are 2 cycles apart in time. So in phase, but not in time at the crossover frequency. So let's go back to the textbook example where we have overlapping phase traces with matched slopes. Let's store this guy and call it 0 cycles offset. Then let's go to half a cycle polarity inverted, which is also in phase but half a cycle apart. Let's sort it as half a cycle offset. And then let's go to the next instance, which is no polarity inversion but 1 cycle or 360 degrees of phase shift, which is this guy with increased frequency response ripple. So this is 1 cycle offset. And then let's go to 1.5 cycles, which is out of phase, but if we flip the polarity, is in phase again, but 1.5 cycles apart. And we can see more severe frequency response ripple throughout the crossover area. And finally, let's take out the polarity and go to 2 cycles or 720 degrees of phase shift and store this as 2 cycle offset. So there you have it. You can see that with each half cycle additional offset you get more and more frequency response ripple, and you will not be able to hear this when listening to a single sine wave. So let's demonstrate that this is very much true. If I skip over to this fragment, we will hear a 100 Hz sine wave, and currently we have summation because there's no offset. But let's see what happens when we go to half a cycle. That should sound like cancellation, because both signals are now half a cycle apart. And if we flip the polarity, then we can hear summation, even though we are half a cycle apart. That is because the polarity flip, changing plus and minus, turned out of phase, in phase again. So let's go to the next instance. Let's listen to cancellation, take out the 5 milliseconds and go to 1 cycle time offset. We are now 360 degrees apart, in phase, but 1 cycle out of time. And for those that are wondering, that I'm doing over here in the corner is listening to the recording, but there's a huge delay, so it's very distracting to listen to my own voice with the delay, but I'm just checking that everything works according as planned. So next instance would be 1.5 cycles, and this would be cancellation again. However, if we flip the polarity, then cancellation turns into summation again. We're in phase, but 1.5 cycles apart. Okay, final instance is 2 cycles apart, 720 degrees of phase shift, no polarity inversion required. This is in phase, but 2 cycles apart. And this is the interesting thing. If we go to 3 cycles or 30 milliseconds, we still have summation. If we go to 40 milliseconds or 4 cycles, we still have summation, and it sounds identical. This is 5 cycles or 50 milliseconds of time offset, and we still have summation. 6 cycles, 7 cycles, 8 cycles, and 9 cycles. So when I went back from 9 cycles to 0 cycles, you did not hear a change. And this is the nature of phase. As long as both signals are present and we are in phase, regardless of how many cycles we are apart, we will have summation. And the same goes for the out of phase, the half cycle offset, which is now cancellation, but when we flip the polarity, it will be summation. This is half a cycle apart, out of phase, but thanks to the polarity inversion, we are in phase again. In phase, but not in time. And this is half a cycle, and this is 1.5 cycle, 2.5 cycle, 3.5 cycle, 4.5 cycle, 5.5 cycle, 6.5 cycle, 7.5 cycle, 8.5 cycle, and finally 9.5 cycle. That is 95 milliseconds. That is almost 30 meters or 90 feet of misalignment. So, as you could hear, there's quite a number of instances or iterations of polarity and time offset where we can have summation. And when you listen to a single sine wave, who is to know that you are within the right cycle, the right amount of time offset, with matching slopes in phase and on time, and not just in phase but possibly not on time. And this is the danger when you try to align main speakers to subwoofers by ear and listen either for cancellation, thinking that you are in phase and on time and then flipping the polarity, or listening to summation while you are adjusting the delay to either the main speaker or the subwoofer, because you're not exposing yourself to the neighboring frequencies. And this is where Michael Binknell's warbles come into play, which is a superior signal, and it sounds like this. And this is a sine wave that is being swept around the crossover frequency. In this case, this is the 100 Hertz warble, and it goes up and down by 40 Hertz. So it's sweeping from 60 through 100 to 140 and back. It goes up and down, up and down. And this signal at least exposes us to all frequencies of interest. And if our phase traces aren't overlapping, if we do not have matched slopes, then hopefully these frequency response ripple that we saw will become audible, telling us that we are off by an X amount of cycles. So currently we are listening to the textbook example with matched slopes and overlapping phase traces. But let's see what happens to the signal when we start to purposely misalign things. So let's start again by half a cycle time offset. And now you should hear a gap throughout the crossover area. Okay, so let's flip the polarity and turn out of phase into phase. So now we have summation again, but we're looking at this guy, the blue guy. We are in phase at the crossover frequency, but we do not have matched slopes, and this will result in frequency response ripple, which is currently very benign, about 1.5 dB to half a dB at the other side. So this is really hard to hear, even when listening to a warble. So next up is one cycle out of time, but in phase. That would be this guy. Now let's compare this sound with the correct one. So this is how it should be, and this is what it sounds like when we are one cycle out of time. And now we have frequency response ripple of about 3 to 4 decibels over here, and 2 decibels, 2.3 decibels over there. And this is hopefully more audible. Try to listen for those dips. They're hard to spot, but if you pay attention, they're there. So next up would be 1.5 cycles, which starts out as out of phase, but if we flip the polarity, then we are in phase again, but 1.5 cycles apart. Sorry. Again, try to listen for those dips. So next up would be 2 cycles apart, no polarity flip. Now you can clearly hear this W action, which is this guy, with minus 6 dB dips to the left and the right of the crossover frequency. So I will go through all instances again, and then we will listen to something else. So this is 2 cycles apart. Let's go to 1.5 cycles. Out of phase, in phase. One cycle apart. Let me restart the warble. And finally, let's listen to half a cycle apart, but with the polarity flip. So this signal is already more suitable when you do not have time to turn on the analyzer, to listen for overlapping phase traces with more important matched slopes. If we listen to a single sine wave, we do not get to detect this issue because we're not exposing ourselves to the neighboring frequencies. And the warble is, for that reason, a more suitable signal. So let's do the experiment one more time using music as the source. I tried to download a track royalty-free by bensound.com with some percussive movements on drums and some bass guitar, so that we have a lot of stuff going on in the crossover region, the very area that we're trying to align. So let's hide these guys and turn on the analyzer again using music as the source and listen to some music. So currently this is our textbook example. Now let's go to the other instances. So this is half a cycle apart, only 5 milliseconds. It's hard to tell whether something is wrong. Okay, let's go to the next instance, which would be one cycle apart. 360 degrees of phase shift, in phase, one cycle out of time. So, next instant, 1.5 cycles in phase, 1.5 cycles apart. And finally, we'll do the 2 cycle apart example, where we are in phase at 720 degrees or 2 cycles out of time. And now the double timing on the kick drum starts to become really apparent. This is also 20 milliseconds almost 7 meters or 60 feet of misalignment. So let's listen to 3 cycles of misalignment. Five cycles. Six cycles. Let's listen a little bit more to that really hard to spot half a cycle offset. One cycle offset. And also here you can spot the double timing. It's hard to tell, but if you listen to the harmonics of the kick drum, you can tell that something is off. And I think that most of us should be able to spot this amount of misalignment. So guys, thank you for watching. That concludes the video, and hopefully shows you the importance of having matched slopes. Otherwise you get this thing which is called frequency response ripple, because you're in phase at the crossover frequency, but can be anything from half a cycle up to a number of cycles apart, in combination with either a polarity inversion or not. And as we saw, listening to a single sine wave will not reveal this issue. That's why we use the warble, if we do not have time to open the analyzer. You can download the warbles at my website with courtesy of Michael Bink-Knowles. It's the 80 Hz warble going from 60 to 120 to 80 to 60 to 120. There's the 100 Hz warble, and if memory serves, there's the 125 Hz warble, which goes up and down by 40 Hz as well. You can also watch the video here, this time with voiceover, or at my YouTube channel. Thank you for watching, and see you next time.